Hello everyone, welcome to the next lecture here. It's on one-sided limits. Now we know that ordinary limits are two-sided. What that means is that when we have, say, a graph that is like this, something like this, and if I was focusing on the limit at this point, C, okay, so if you approach C from the left and from the right, correspondingly on the graph, you approach it from the left and from the right, we see that it actually corresponds to a limit L. So that's when we say limit, let's call this red graph as f of x. Then I will say limit f of x as x approaches C is equal to L, right? So from both directions does it point to the same limit. So ordinary limits are this way. So if a function fails to have two-sided limits, it may not it may not point to that same L, but it could have a one-sided limit and point to L just from one side. Okay. So you can see that if the function fails to have two-sided, we can still go with one-sided. And so if we approach it from the left, meaning if we approach C from the left, it implies that we have a left-sided limit. Sometimes it's also known as left-handed limit, right? Or left-handed limit. Now, remember the notation for this would be minus. I'll shortly give it to you in the full format, but remember minus. When you approach from the left, it takes a minus as the symbol for it. When we approach the value C from the right, then we call it as the right-handed limit or right-sided limit. And the symbol for that will be a plus. Now, for convenience, I'm going to call this as left-handed limit as LH, okay? And we'll call this as the RH, right-handed limit. So if I were to use the notation, then left-hand limit would be limit f of x as x approaches C. If I simply say C, it means we're approaching from both sides. But if I use the minus sign as a superfix, above it, so x approaches C minus, that means we approach C from the left, and that may go to a limit L. And we can have, for the right-hand limit, it will be limit or lim f of x as x approaches C from the right with a plus sign on top, and that could go to some other limit m. I'd like to illustrate this using an example. Now take this function y equals x over x bar. Now this is because of the I said x bar, I'm sorry, x over absolute value of x. Absolute value of x, we know, is by nature, by definition, a piecewise function because it has the V shape, right? Remember? It has that V shape. So V is formed by two separate lines, two pieces. So because of that, this function has that effect on it where you have two pieces. So it's a piecewise function. Now, if we were to focus on 0 and we approach 0 from the left, we see that only one piece appears on the left, and that piece kind of stops at 0 with an open circle. If you approach 0 from the right, you have only one piece on the right-hand side that's happening above there, and that approaches value 1 as we get closer to 0 on the x-axis. So you see that break or that jump there. And clearly, you do not have the as we approach 0 from the left and the right, we do not have one same value to which the graph approaches. Instead, it approaches two separate values. So this is a case of one-sided limits. Okay. So we don't have a two-sided limit. So the way I will define this is, I will say limit y, lim y as x, because those are the players, right? X and y. If they have s and t, you have to use s and t. Or if you had f of x and x, then it's f of x instead of y. So x approaches 0. As we approach 0 from the left, which means I'm going to bring a minus there, we see that that's going to give me a -1, because that's where the graph points to. Okay, left-handed limit, which means we approach from left. Again, notice the language. We say approaches from the left, not to the left, because then that will change things, right? They change the direction. So we approach 0 from the left. So approach 0 from the left. That's what we mean by that minus sign. Okay. And this would be limit y as x approaches 0 from the right will be a positive one. That's on the top. And this is a right-hand limit, which is when we approach 0 from the right. Now, clearly, they do not point to the same value, and that is kind of justified when you bring the minus and the plus, because you are indicating that it is a one-sided limit. Now, because of the presence of one-sided limit, we can also kind of conclude and say that if both the left-hand limit and the right-hand limit, if they point to the same value, we can then say that the function has a limit, right? So let me write that down here. And so that's what we have. We can clearly see that when we say a function has a limit, we are not specifying left or right hand, indicating that it is a two-sided limit. So if we were to again define this using notations, so limit f of x for some function f as x approaches c, if that is equal to L, you can break it up into the left side and the right side limit. So it implies and is implied by the fact that limit f of x, x approaches c from the left is equal to L, and, that's important, limit f of x as x approaches c from the right is also equal to L. Okay, so if you can split up the limit into left-hand, right-hand side, if they point to two different values, then we have one-sided limits. If they point to the same value, then we establish that the function has a limit, which is a two-sided limit. Now, the one-sided limit can be illustrated in this example, these two graphs. So if you can see the first one, it is limit of f of x as x approaches c from the right is equal to L, right? So we are looking at c and we're approaching from the right. You see the arrow getting towards c from the right. And, this L here would mean this height, L, right? So you can see that this end, your graph basically ends here. That's the reason why you don't have a right-sided limit, because if you approach c from the left, did I say right-sided? No, we don't have a left-sided limit. Now, if we approach c from the left, we see that there is no graph occurring on the left, and therefore we cannot approach c from the left, and therefore we are to deal with just the one-sided limit there. Likewise, if you come to the second graph, B, right? So you have your x values approaching c from the left. So you have the left-sided limit. But you don't have the right-side limit, because if you approach c from the right, there is no graph happening on the right of c, and therefore that's the reason why we don't have a two-sided limit. Now, if I were to adjust this a little bit, and then if I say it goes somewhere like this, then we have both sides pointing to the same value m, and therefore I can say limit x, f of x as x approaches c from the right will also be m. If that's the case, then we have a two-sided limit, in which case we would just say limit f of x as x approaches c, no plus or minus, equals m. Right? These two together will give you this. So what we realize is that we have situations where your graph need not go endlessly, and it can have one end limited and the other end going endlessly. If that was the case, then at that point where it ends, you will only have a one-sided limit. Okay, how about this function? This is a semicircle, right? It's half a circle. And it's illustrated by, it's given to you by this equation, y equals square root of 4 minus x squared. Now, if you look at this, the domain is -2 to 2, right, included. And so what we see here is if we were to approach 2, okay, this is 2, so let me use a green here. If we want to approach 2 from the left, we can see that the corresponding function value for that will be 0, right? Because the graph points to the 0 as we approach 2 from the left. So how do I write this? I can say limit y as x approaches 2 from the left, so it's a minus. Or you could just write it in the expanded form as 4 minus x squared as x approaches 2 from the left is 0, right? Now let's talk about approaching 2 from the right. Is that possible? If I approach 2 from the right, I have to look for the function to the right of 2. Well, the domain is from -2 to 2, so we don't have anything past 2, beyond 2. So the right-hand limit for x approaching 2 does not exist. Okay, so this will be my left-hand limit. Now I go to the -2. If I approach -2 from the right, I find that that value corresponds to a 0 on the y-axis. Okay, so limit y as x approaches -2 from the right. So it's a -2 with a plus suffix. Or I could write it as 4 minus x squared for the y. X approaches -2 from the right is also 0. That'll be the right-hand limit. So you have to be super careful here, okay? Because your answers are 0 and 0, you can't just say there is that limit, the function has a limit at a point, because you really have two different points that we're considering. We're looking at 2 and looking at -2. They both point to the same 0, but they are not the same value that we're approaching from the right and from the left. Okay, so there are two different values that we're approaching, one from the right and one from the left, both giving us the same value, the same limit, 0. So we want to be cautious here. Okay. Let's take a look at this graph and see what happens for each value of x. Okay. So we're going to look at each value of x, meaning 0, 1, 2, 3, and 4. Okay. At x equals 0. Let's focus on that. Now, we are going to approach from the left and from the right separately. And if they get the same values, then we'll say the limit exists. If it doesn't, then we'll say the limit does not exist. Okay, so I'm going to show you with the example for the first one. Now we're going to approach x equals 0 from the left. Okay. This is a function f of x. They didn't tell us what it is, so we'll just write f of x. As we approach x from the as we approach 0 from the left, so 0 minus. Okay, we don't have any value, so no value. But the better way to write this is to say it does not exist. Okay. A value does not exist, meaning the limit, the left-sided limit, does not exist. And an easier notation is DNE, does not exist. Okay. All right, let's approach 0 from the right. Limit f of x as x approaches 0 from the right with a plus. Then look at your blue piece that's approaching from the right. Several pieces, but this is the only piece that approaches 0 from the right. And what we see is that the graph gets closer and closer to 1. So that's equal to 1. Now we need to see if the limit of f of x from the left and from the right. So and just from the left and if from the right are the same. Are they equal? They are not equal. So I put the not equals, and this implies limit f of x as x approaches 0, just 0, which means both sides, d and e, does not exist. Because the left hand and the right hand limits did not match. All right, so this is how we're going to approach each value. Okay, so I'm going to remove that. Then let's take a look at 1. Let's approach 1 from the left. So near x equals 1, what happens? Limit f of x as x approaches 1 from the left. So 1 with a minus equals. And then what we see is the corresponding piece, right? That one approaches 0. Again, please bear in mind that at 0, the function itself is not defined. But that's not our worry. We've seen that in limits, that we're not worried about the function at this point. When we talk about limits, we're just worried about the value it gets closer and closer to. Well, at 1, it is not defined. But if we get closer and closer and very close to 1 from the left, we see that it actually approaches 0. So we got that. And limit f of x as x approaches 1 from the right. So let's go here. We want to approach 1 from the right. So look at the piece that gets closer to 1 from the right. That's the one that gets close to 1 from the right, and that value actually points back to a 1. So once again, we see that the left-hand limit is not equal to the right-hand limit. Or the left side limit is not the same. So this implies that limit f of x as x approaches 1 does not exist. So they have to be equal, even though they went to nice values individually. The function does not have a limit at as x approaches 1. Okay. What about x equals 2? So we are focusing on x equals 2. So get rid of this. Now, as we approach 2 from the left, we see that this piece of the function, right, approaches 1. Now, don't get confused with this dot here, okay? That's a single point, which means we really don't have any function approaching from the left or the right. It's a point. So we do have a function piece that does approach from the left. So it travels from the left, and that is pointing to the value 1. Yeah. And let's go to the right-hand side. So we approach 2 from the right, and that's the piece that approaches to the right. Again, remember that you are not looking at where the function is defined, because f of 2 is 2. That's where the closed circle is. So don't worry about the open circle. We're trying to see if we are able to approach it on the function, and that also points to 1. Okay. 2 from the right is equal to 1. Okay. So I just say never mind if f of 2 is equal to 2, that solid dot. Okay. So this implies limit f of x as x approaches 2 from the left is equal to 1, which is the same as limit f of x as x approaches 2 from the right. Because these two match, this implies that we do have a limit as x approaches 2, which is equal to 1. So the limit exists. I just say limit exists if you were to write it in words. Took a while to write that. Okay, now we'll look at 3. As we approach 3 from the left, this function piece also goes from the left and it gets closer to 2. And as we approach 3 from the right, that piece also gets to 2. So let's write that out here. X approaches 3 from the left. Since left hand limit is equal to the right hand limit, it implies that limit f of x as x approaches 3 exists and is equal to 2. Let's go to the last one, which is 4. Let's approach 4 from the left. You see that the piece that approaches towards 4 from the left approaches 1, right, corresponding to the y-axis. But if you were to approach 4 from the right, there is no function piece to the right of 4, so we do not have any function piece there. Just like the 0, or to the left of 0, we had no function piece. Likewise, to the right of 4, we have no function piece. So this is clearly a one-sided limit. So let's come over here and say at x equals 4, what happens is that the limit of f of x as x approaches 4 from the left pointed to a 1. However, the limit of f of x as x approaches 4 from the right, dne, does not exist. Cool. This implies left-hand limit is not the same as right-hand limit. You have to give this reasoning. You can't automatically assume that the person who's looking at it knows what you're thinking. So you have to write it out. And then you go further and say, limit of f of x as x approaches 4 does not exist. So technically we have in between 0 and 4, f of x has limits at, so it didn't work at the first one, second. So f of x has limits at 2 as x approaches 2, as x approaches 3 only. Okay, these 2 points. Let's take this graph. This graph is y equals sine 1 over x. So our question is, what is, or find the limit of sine 1 over x as x approaches 0. That's our question. So just investigate what happens very close to 0. In fact, it'd be nice if we could use a graphing calculator. When you're given a problem like this and you're given the graph, to really see what's happening, sometimes it's nice for you to enter this equation in the graphing calculator and look at the graph. Well, what you'll see is near 0, it is very blurry. So if you get closer, if you zoom in and go closer and closer, it actually, it's never ending, because you will see that it's getting really busy. The graph is going up and down, oscillating very rapidly near 0. So what that really tells us is, technically, it's going up to 1 and down to -1. And those are the two. That's kind of its limiting values. It's just going up and down there. So near 0, the graph, fluctuates. So I'll just write that here. Near 0, the graph fluctuates rapidly between -1 and 1, isn't it? So there is no way for us to find, as x approaches 0, we see that the function, there's no particular L that you can come up with to see what happens as we approach 0. This implies there is no single number L, right? Because we're looking for the limit. As x approaches 0 from the left or from the right. That's the case on both sides. So we didn't find the limit. We didn't even find a one-sided limit. So we just have to say this implies limit sine 1 over x as x approaches 0 does not exist. Now take a look at this graph. This is the graph of sine theta over theta. And this is in radians. It's measured in radians. What is the limit when we approach 0? Okay, when theta approaches 0, what is the limit of sine theta over theta? So let me write that out here. So limit sine theta all over theta as theta approaches 0. Okay, what is it equal to? So graphically speaking, so this is 0, right? We are approaching 0 from the left, and correspondingly your graph approaches 1. Okay, so limit sine theta over theta as theta approaches 0 from the left will be a 1. And likewise, if you approach theta from the right, the graph also points to 1 as the value, the limit, which is the same as limit sine theta over theta. Theta approaches 0 from the right. And because both limits are the same, it implies that limit sine theta over theta as theta approaches 0 is 1. This is actually a special theorem. It helps us to find the limit for this particular situation, sine theta over theta. Now, if you think of this, if you didn't have the graph, what you would do is you'll actually, if you use the limit laws, if you plug in 0 for theta, sine 0 over 0, you'll get a 0 over 0 condition. And you'll have to use different techniques to actually come up with a solution for that. And one of the ways we would approach that would be to use trig identities. Now, trig identities would make it a little more complex than you would want because this is in its most simplified form. So then if we were to approach a different way to solve it without the help of a graph, then we have to then fall back on squeeze theorem. We could use squeeze theorem to come up with two other functions between which sine theta over theta is squeezed. And so if we can't find directly two other functions, then we'll have to use geometry and trig combined to get this derivation. And so there is actually a derivation that is given to us to prove this. So just to kind of pique your interest in this, I'd like to discuss that derivation. The proof for the previous theorem is drawn from trigonometry. This is a unit circle, but also from geometry. So here is, I'll give you a general gist of how this is set up. So this again requires a little, advanced understanding of geometry. But if I kind of explain it to you in the trig terms, I think you'll understand this quicker. Now, what we're trying to do is apply the squeeze theorem, the concept of squeeze theorem, and try to set up an inequality, okay? Because that's what squeeze theorem does. So if you look at triangle OPQ, right? OPQ. This is the triangle. And then we want you to consider sector OPA. Okay, it's a sector. It's a portion of a circle, right? It's like a pizza slice. You can think of it as that with a curve. And then we have triangle OTA, the one with the yellow side, right? OTA. Now we can see that this is how they will be, right? In terms of the size of the triangles and the sector. So if you were to find the area for each one of these, area of triangle this, area of the sector, and area of this triangle, that will help you to set it up. Okay, so that's one way. Now I want to quickly use geometry, trig here, to kind of show you that let's kind of point out sine theta. Okay. So this is the angle theta, right? So sine theta is opposite over hypotenuse, isn't it? So that is the opposite side for this triangle. Let me put it down here, maybe that'll be easier. For this triangle, sine theta is opposite, which is PQ, right? That line PQ, the blue line PQ, blue side I should say, over hypotenuse. Now look at the hypotenuse. Hypotenuse is 1 because that's a unit circle. So in other words, let me erase all these things. In other words, this means sine theta itself is PQ, isn't it? So I'm not trying to measure the area. That is one way to prove, but I'm trying to do it simpler for you. If you go to the sector, okay, the sector is this wedge. But if you look at PA, okay, I'll call this arc PA, arc length. We know from arc length formula that S equals R theta. Now theta is here measured in radians, okay? Let me make that very clear. This works only if theta is measured in radians. Only then we'll measure the arc length in terms of the radians. So S equals R theta. And what is R here? The radius is 1, so S itself is equal to theta, meaning the arc length itself is theta. So arc length PA is theta. Okay. And then from this triangle with the yellow side, we have, again, you can think of tan theta. Tan theta is opposite over adjacent, right? So opposite is TA over adjacent is OA. You can see that OA would be the radius, right, of that circle because A touches the circle. So OA would be 1. OA is equal to 1, which means this implies your tan theta itself is equal to TA. Okay. So we can see that PQ, or rather I should say PA, right, the arc PA is in between PQ and TA. PQ is less than PA is less than TA. So you can set it up as sine theta is less than theta is less than tan theta. Do we agree? And so once we get this set up, remember we want to, the whole idea of proving this is to get the sine theta over theta situation. Okay. So what I'm going to do is divide each part of the inequality by sine theta. Here it cancels off, right? It gives us a 1. This will be theta over sine theta. What is tan theta over sine theta? Let's do it here by the side. Tan theta would be sine theta over cosine theta, right? And then you have a sine theta in the bottom. So those will cancel off. So technically you'll have 1 over cosine theta. So let me rewrite this. 1 less than theta less than 1 over theta inverse sine theta over 1 less than 1 over cosine theta. We want it the other way around. We want sine theta over theta. So if you wanted to flip, okay, if you take the reciprocals, that will reverse the inequalities, okay? Reciprocals will reverse inequalities. So 1 over 1 is 1 itself. Reverse the inequality. You get sine theta over theta. Reverse the inequality and flip it. So that will be cosine theta over 1, which is basically cosine theta. So if we kind of rearrange this, it will be cosine theta less than sine theta over theta less than 1, right? Because you want the inequality to be written in a way you can read it. So sine theta over theta is between cosine theta and 1. Now, if you go back to what we're trying to prove that limit of sine theta over theta as theta approaches 0 is 1. Now we use the squeeze theorem idea, okay? And we want to, so this is kind of basically sine theta over theta is squeezed between sine theta, cosine theta and 1. Now we will apply limit theta approaches 0. So I'm going to rewrite this with some space. And I will insert the limit. Theta approaches 0. Limit theta approaches 0. So when I apply this on all three parts, limit cosine theta as theta approaches 0, this whole thing comes out to be 1, right? When you plug in 0 for theta, cosine 0 is 1, less than limit sine theta over theta as theta approaches 0 is less than. Again, this is a constant, so it comes back as 1. So if you're squeezed between two ones, then the middle one that is in between them should also be equal to 1. By sandwich theorem, we see that or squeeze theorem, we see that limit sine theta over theta as theta approaches 0 is sandwiched between two ones, one on the left and one on the right. That means limit sine theta over theta as theta approaches 0 equals 1. Thus proved. Hence proved. So that is how I gave you a derivation for this particular one using combination of trig, geometry, and squeeze theorem. So there is another theorem that we also use, a commonly used one, that I'd like to just present to you here. So that will be limit cosine theta minus 1 all over theta as theta approaches 0 equals 0. Okay. Here again, if you plugged in 0 for theta, you'll get cosine 0 minus 1 over 0. Cosine 0 is 1, so 1 minus 1 will be 0 over 0. So again, using derivation like this, squeeze theorem concept, you will have another theorem. So let me box these two together. So limit sine theta over theta as theta approaches 0 is 1. And for cosine theta minus 1 over theta that approaches 0 is 0. Okay. We'll do a couple of examples to drive home this point. Show that limit of sine 2x over 5x as x approaches 0 is 2 over 5. They've given us the answer. They want us to prove it. So whenever there is a solution provided and we have to verify it, in this case, just like in trigonometry, we will start with the left-hand side and show that that value equals the right-hand side. So we'll take limit sine 2x, over 5x as x approaches 0. And we want to recall that limit sine theta is some angle, right? Over that same angle theta as theta approaches 0 is 1. We just established that. So if I can get sine 2x over 2x, then we know that that's going to be 1. So I'm going to do a little manipulation here and multiply up and down by 2x. So what I'm going to do is I'm going to separate the sine 2x from on the top and the 5x on the bottom, right? I separate them and I'm going to insert a 2x here and a 2x there, right? Up and down. I multiply up and down by 2x. So what happens is, you can see it that way because I just wanted it to look visually cool. But basically what you're doing is you are keeping the numerator and the denominator separate from each other so that you could have the 2x matching. Now, if you find that a little challenging to follow for some reason, then all I'm trying to do is multiply up and down by 2x. So let's pull out the 2 over 5, which is a constant. And then we have sine 2x over 2x. But we know that this whole thing with the limit. This whole thing is equal to 1 from the condition, the rule that we saw. So basically, it is 2 over 5 times 1, which is 2 over 5, which is the same as your right-hand side. Thus, we showed that the left-hand side is the same as the right-hand side. In fact, I can also use this show that condition to prove that limit cosine h minus 1 over h as h approaches 0 is equal to 0. This was the very theorem I showed you previously. Instead of h, we had theta. We can still prove this using the sine theta over theta that we just did in the previous problem. Okay. So what I'm going to do is use the half angle formula from your trig identity, and that says cosine. In the formulas, you probably have them as alpha and beta, but here we have the angle as h. So cosine h is 1 minus 2 sine squared h over 2. So we want cosine h minus 1. So cosine h minus 1, subtract 1 on both sides, will be negative 2 sine squared h over 2. So I'm going to use this on my left-hand side. So the left-hand side is like this, cosine h minus 1 over h approaches 0, and replace the cosine h minus 1 with negative 2 sine squared h over 2 divided by h. Okay. Now for convenience, feel free to substitute. So it's easier for me to see it as theta. So I'll say let theta be equal to h over 2. Okay. So what we're going to do is, again, mathematical manipulation, where we will rewrite this as negative, just this function, negative sine squared h over 2 over, this 2, I want you to bring this down here. That means that will become h over 2, isn't it? So it's easy if you saw it as with a substitution. So I'm going to call h over 2 as theta. And so if you see the substitution, it's a whole lot easier to handle. Okay. Well, when h approaches 0, we have it like you can replace it with theta as well. Okay. So that's going to be negative sine squared theta over theta. That's how it looks. Right? Now let me pull the negative outside because it's like a constant. It's like a negative 1. And sine squared theta, I'm going to write it as sine theta times sine theta. Right? That's sine squared theta. And one of them can have the theta in the bottom. Right? That's how it can be. You can't have the theta for each one of them. That will make it theta squared. So only one of them. And we know that this one, again, is equal to 1. And this one, sine theta, will also get a 0. So just before I do that, let me separate them so we can see how it works. So sine theta over theta, by product rule, this one also will get a limit sine theta. Okay. And now I can show that this is equal to 1. And when you plug in 0 for theta, sine 0 is 0. So what we have is negative 1 times 0, which is 0, which is our right-hand side. Thus, we prove that as well. So you will have situations where you'll be asked to prove, always start from the left-hand side. And if you have a previously known formula, you might want to use that like we did here. Precisely the sine theta over theta helped us through all these problems. We'll do one last one. Find limit tan t secant 2t over 3t. So this is not a proof situation. We have to find the value. Okay. So first of all, when you have the tan and the secant, we want to rewrite them in their basic form, which is the sine and the cosine. So tan is sine t over cosine t. Remember to use the same function you see. And secant t is 1 over cosine 2t. Secant 2t is 1 over cosine 2t. It's the reciprocal of cosine over 3t. So if we were to, you have layers of fractions there, right? So please try to simplify that. So this is the whole thing, numerator over 3t, right? Which is basically 1 over 3t times sine t over cosine t times 1 over cosine 2t. Agreed? Now 1 over 3 out of the 1 over 3t, 1 over 3 can be pulled out, it's a constant. So that's limit 1 over t times sine t over cosine t times 1 over cosine 2t. Remember again, when we apply t as 0, wherever cosine is, it becomes cosine 0, right? 2 times 0 is also 0. So in both these cases, cosine is in the denominator and it turns into a 1. So it's well defined, not a problem. Now we do have sine t and the t. So I'm going to again use algebraic manipulation to rearrange them as sine t over t times, this limit is for each one of them, right? Over cosine t times 1 over cosine 2t. Notice how I combine the sine t and the t together as a fraction. So you can move them, right? So I got this as a fraction and I kept the cosine t and the cosine 2t as into separate fractions. Now it's time for us to apply the limit for each one of them because it's a product. You can use the product rule to apply limit for this times limit t approaches 0, 1 over cosine t times limit t approaches 0, 1 over cosine 2t, which is 1 over 3 times, again, recall what happens here, this one by that theorem is equal to 1. So I'll say that is 1 times 1 over 1, because when you apply 0 for t, you get 1 over cosine 0, which is 1 over 1, times 1 over cosine 0. 2 times 0 is 0 again, so cosine 2t is also 1 over 1. So basically it is 1 over 3. So the answer for that problem is 1 over 3. So that brings us to the end of one-sided limits. I hope you enjoyed it. I will see you in the next video.